Hi, welcome back to our series on concepts of programming languages. Today we'll learn about functional abstractions. So briefly, here is our agenda. We look at why we need functional abstractions as a way to perform code reuse. We look at how these functional abstractions are defined and what the difference between definition and declaration is. And we look at also how these functional abstractions in various languages, they can be invoked or called. And then we look at what are side effects. We looked at that briefly with our session on expressions. Essentially, we look at what the impact of executing these functions have on your external environment or other parts of your program. Then we'll also look at how the referencing environment looks like when we define variables inside your functions. We briefly looked at it already in our course on variables or in our session on variables. We'll look at them again in a little bit more detailed with the perspective of functions in mind. Then we'll look at the semantics of functions themselves. Of course, we'll not look at the complete details of all kinds of functions, methods, and procedures because they vary greatly between different languages. But we'll look at how you can define operational semantics for functions and what that means to the side effects and so on and so forth. One key aspect of functions are parameters. We look at different kinds of parameters and also how these parameters are passed, different ways they are passed. And then we'll also look at a couple of different variants of functions themselves, right? And at the end of the session, we'll also look at a very specific type of nested functions called closures. Let's begin. So functional abstractions are means that are provided by programming languages to promote reuse of certain code segments, right? There are many general properties of functional abstractions that most languages adhere to. One of them is that generally functions have one entry point, and every time a function is called, the program execution shifts from the normal program execution is suspended, and the control is given to the function itself that is being executed based on the various configurations and parameters that are provided to it. And after the execution of the function is complete, then the control is returned to the caller itself. It means that it's not just the control is not going to go into an ad hoc part of your system that you cannot control anymore, right? I kept using the word functions and functional abstractions interchangeably, but there are different kinds of abstractions provided by different languages. Languages like C and Python and Haskell provide functions, which essentially are very close to mathematical functions. They're a fundamental thought in computer programming. It's used to calculate something if you give it an input, and hence the name relates to the same name for mathematics, which is functions. They can either be user-defined or predefined. Essentially, they are used to perform a specific task, right? Procedures, on the other hand, are similar to functions and can be, some languages use them interchangeably too, but conceptually the difference between a procedure and a function is that a procedure is simply a particular set of instructions or command that just need to be executed in a block. So procedural languages like SQL support procedures. In most languages, the implementation of functions and procedures are rather similar, but the difference is mostly just conceptual. Methods, on the other hand, are similar to functions, but they are for the object-oriented world. Languages like Java and Smalltalk provide methods which are essentially functions that are bound to a particular type or particular object, right? So let's look at how functions can be defined. Essentially, a definition of a function is a way for the developer or the programmer to provide meaning to these functions. In general, a definition of a function has various components, and how these components look like syntactically and also mean semantically vary greatly between different programming languages. But let's look at how functions are defined in the world of C. Essentially, a function definition first binds a function to a name. Essentially, this is what you use to call the function later on. We'll see it in the invocation part. It has parameters which are used to configure how the body, the function body, which essentially said, this is the task you need to perform, but you have to configure this to these particular formal parameters. There is another kind of parameters which we'll discuss when we look at function invocations. But briefly, these are the various components a function definition needs to contain. It needs to have a name, it can optionally have parameters which decide how the execution or computation of the computation inside your function takes place, which is then specified in the body. Functions also have return types. And the parameters can also be bound to types, but this is not true for all languages. Some languages simply infer the type based on the computation and based on the parameters that are passed. So that's how you define, how you provide meaning to a function. Declarations are also similar to definitions, but you can think of them like small definitions with particular information left out. These are generally used to used by your compiler to perform checks, or also these help your compilation process be more modular when you don't need all of the information of your function, especially the body of the function, for the compiler to perform certain computations, right? So essentially, declarations are small versions of these declarations. They bind the function name to a subset of the function's attributes. For example, mostly the number of parameters, the types. As I mentioned before, these types can also be inferred in certain languages. So here is an example of a declaration of the multiply function that we saw before. And finally, we have invocations, which help the developer to call or tell the compiler that, hey, I want to perform the computation that this multiply function allows me to perform, but perform the computation with these two parameters, which are the actual parameters, which are bound to the formal parameters. We will look at different ways of how these actual parameters are bound to formal parameters. They can be very different based on what kind of languages do them and what kind of parameters you pass on. So here you're simply invoking the function multiply to say that give me the value of 100 multiplied by 32,768, and then the returned value is then stored on this stored in a variable v. So we looked at a specific function, and we also looked at invocations. But if you remember from the previous session on expressions, there was this concept of referential transparency. To recollect, referential transparency essentially means that your expression does not have any side effect. Meaning, if you execute the expression any number of times with the same parameters, the state of your program does not change at all, meaning they have no impact outside your expression. This concept can be extended to functions too. Let's look at a couple of different functions and see if they are referentially transparent or not. Here is the function multiply that we saw. The first function on top is the function multiply that we saw in the previous slides. It essentially takes in two parameters, a and b. It multiplies the result and returns the result. Is this function referentially transparent? Yes, it is referentially transparent, because if you provide the same values of a and b, the return value will always be the same, and the state of your program does not change at all. There is no influence from this function to any variable or essentially anything outside the function itself. But on the other hand, look at the function below, which essentially increments the value of c, which is not local to the function itself. It's a static variable that is defined outside the function. Every time you call next, the value of c changes. It is incremented by 1, and this means that this function below is not referentially transparent, meaning this function has side effects, right? Let's try to formalize this a bit based on the operational semantics that we saw before. The semantics looks something like this. A function with any number of parameters in the state sigma is evaluated to v, and the state changes to sigma star based on whatever your function does to the state of the program while it is executing, right? So Formally, sigma to sigma star is defined as the side effect. The side effect could be updates to non-local variables, as we saw before. It can be file reads and file writes, which changes the state of files, state of files which are outside the program. It can also be network accesses, which has a side effect on something completely outside your system itself. Generally, the terminology pure function is used to define functions that are free of side effects. Formally, this essentially means that whatever you do or whatever your function evaluates to, the state sigma, which was before the execution of the function, and state sigma star, which is the state of your program after the execution of the function, are both the same. So now we have looked at side effects for functions and referential transparency of functions. Let's look at how local variables inside the function are dealt with from the perspective of memory. If you remember before, the referencing environment depends on where variables are stored depending on which part of the memory they utilize, how they're allocated and deallocated. In most modern languages, variables that are local to functions are stored as stack dynamic local variables. You can refer to the session before on the advantages and disadvantages and the methodologies with which they are allocated and deallocated stack dynamic variables. But essentially, the advantage of using stack dynamic local variables to deal with variables that are local to functions are that they permit recursion, which is very important when you're supporting functions. The second advantage that the storage sharing is possible among some functions which refer to the same stack is no longer that much of an advantage, because in today's world, memory is big enough that we don't have to worry about variable sharing. The disadvantages are that allocation, anytime you're storing variables on the stack, you need to worry about the allocation, deallocation, and also the time it takes to initialize these variables. The other disadvantage is also that the addressing is indirect, meaning the address of this variable is relative to the stack pointer or the function pointer. This is a disadvantage. The third disadvantage is that the variables are not sensitive to history, meaning you have no track of what variables were, what return values what values your function returned for a previous call when you are making a new call. Such history sensitivity is needed, for example, when you're calculating pseudo-random numbers, meaning your function calculates a random number and you want to make sure that you don't return the same random number for the second call, right? For example, this kind of things would be useful when you are working on when you're trying to get the next song in your playlist in the shuffle fashion. But as mentioned before, most modern languages use stack dynamic local variables to handle variables that are local to their functions. Again, as mentioned, C++, Java, Python, C# all use stack dynamic variables for their local variables. Languages like C also provide the opportunity that you can define variables inside your function which have global scope and are dealt with dynamically by simply using the static keyword. Yes, now that we have looked at functions, their definitions, how they are invoked, and basics of parameters, I mentioned before that parameters are not that simple, meaning there are different types of parameters, there are different ways you can call these parameters. Let's first look at different types of parameters. The first type of parameter is called the default parameter, meaning that you provide a default value for this parameter. Here in this function which increments x by step, you've given a default value of 1, which means if you do not provide the second parameter, x would be simply incremented by 1. Here invoking increment with simply 2 just increments it by 1. It takes in the default value of step and performs the addition and then returns the value. You can override the default value by providing a proper normal invocation like we saw before, providing both the values in the order, saying increment 3, 2 provides results in 3 plus 2, which is 5. The next kind of parameters are keyword parameters. Here you do provide default values, But when you're invoking the function, you explicitly say which parameter by name or keyword relates to which value. The advantage of this kind of parameters are that you do not have to worry about the order, and when reading the function invocation, you can clearly make sense of, without going into the definition, you can understand what the function is going to do. Here, let's look at an example of keyword parameters from OCaml. Since we've not discussed much examples from OCaml, I'll go through this in a little bit more detail. So here is a function roll dice, which takes in two parameters, the number of sides of the dice and the count. Essentially what this does is it simulates rolling a dice with x sides, here 6 sides by default, n number of times, which is provided by count. So count number of times. What it essentially does is it starts by assigning the result to be 0, and then for count number of times, it adds result with 1 and then a random value between 0 and sides minus 1. So how keyword here there are 3 examples of how you can invoke functions with keyword parameters. First one, you can simply say, I want to roll dice. This simulates rolling a one die, which is 6-sided, one time, right? And if you call it with the value 3 to the parameter count, simply assigning the keyword count to 3, you can see the function would simulate rolling a 6-sided die, because the default value for sides is 6, 3 times, right? And the third variant of the invocation, where you roll dice with count 2 and sides 10. What's interesting to note here is that the parameter order is reversed, and it does not matter with keyword parameters, right? So when you roll the dice, so the last invocation essentially simulates rolling a 10-sided die 2 times. So these are keyword parameters. We've seen default parameters and keyword parameters. Now let's look at the third and not final. There are other kinds of parameters too, but the final kind of parameters that we'll see in today's session, which are variable parameters. Most modern languages support variable parameters. Essentially, variable parameters are parameters where the length is undefined. Here is an example from Java, where here you have a function int count, which takes in any number of args of type object, and it essentially calculates, it returns the length of that length of the number of parameters. So if you pass in count 1, 2, 3, it would return 3. If you pass count 0, 0, it would return 2. Java translates variable parameters to arrays. Other languages like C use more complex mechanisms. We'll not get into those, but the point is that variable parameters allow you to define functions which take in any number of parameters and you don't know it in advance, right? So now that we've looked at different kinds of parameters, let's look at a couple of different kinds of functions before we look into how parameters can be passed, right? The first kind of functions are indirect functions. Here you are essentially passing a function as a parameter, or you can treat them like any other variables, right? Here is an example from Python where apply I takes 2 parameters, a parameter function f, which is an indirect function, and a list. And what it does essentially is that it creates a result, which is again a list, and it goes through, iterates list, the length of list number of times, and for each iteration, it appends the execution of function f with 2 parameters, which is the value of list at I and then the offset I itself, and then it finally returns the result. So to provide a visualization of it, if the list is L0, L1, L2 till Lk, the result would be simply a list where each entry in the list would be the result of invoking f on Li, comma I. So it would simply be f invoking f, the result of invoking f with L0, 0, and then the next element would be f invoked with L1, 1, so on and so on till the last element of result is simply the result of invoking f with Lk, k. A couple of examples, couple of actual instances of such invocations where you can see why it's useful. So if you call apply I with multiply and provide the list 2, 2, 2, 2, what it's going to do is essentially create a result list which is going to apply multiply on each of these parameters along with the offset. So the first result would be 2 multiplied by 0, 0, 2 multiplied by 1, which is 2, 2 multiplied by 2, which is 4, and finally 6. The next function, next application, next invocation of apply I uses the function max, and you provide 1, 1, 1, 1. Essentially what it does, it is compares each element of the list with the offset and sees if it is, whichever one is the maximum, it returns it. So the first two values are 1 because the first two offsets are 0 and 1 is the maximum of 0 and 1. But every other time it's just going to simply return the offset because every other offset is greater than 1. So here is an example of indirect functions and how it is supported in Python. And these are powerful mechanisms too, depending on what kind of computations you want to perform. The other kind of functions which can get quite complicated, but we'll discuss it briefly in today's session, are called nested functions. Essentially, nested functions are functions which are defined inside other functions. Here, let's look at an example. You have function f, which inside it has a local variable 1, and then inside it actually has a definition of function g, which prints the value of x. What x it prints depends on what kind of binding it is, which we'll see. And essentially, this function returns another function g, which simply prints x. Again, we'll see what the value of x is based on what kind of binding we use. So in the same program, we have another function h, which takes in a function p. As we saw before, it's an indirect function here. And inside it, there is a local variable 2, and the result of invoking h is simply to invoke p, right? What p refers to, what p is, depends on how h is invoked. So finally, in the main block, we have a variable x, which is assigned to 3, and h is invoked with f, right? So what this essentially means is that so what p refers to depends on how h is invoked, right? So we know from before that f simply returns g, which means g is what is bound to f when h is being called, and this is what is essentially p refers to. So ultimately, the invocation h of f is simply the result of invoking g. But since g prints x, we need to know which of these three x's g is going to utilize. And that depends on whether, of course, p is essentially referring to g. What the value of x is for this invocation of g depends on what kind of binding we use. So the first kind of binding is called shallow binding. Essentially, the first kind of binding is called deep binding. Essentially, deep binding gets the value of whatever the variable is from its definitions. Languages like Python, OCaml, and Haskell use deep binding. Essentially, this means that the definition of g is nested inside the definition of f, which means the value is 1, so it's going to print 1. The other variant is to use a shallow binding. Shallow binding uses the invocation point, or where it is invoked. In this context, meaning h of p is the function that invokes g at this point. So it would use the value at that point, which means it would print x, right? Variants of Lisp use this variant. Versions of Lisp use this variant of binding. There is another binding that is thrown around in literature. I cannot think of any examples, but if you are able to find examples of ad hoc binding, then you can keep me posted on it. So essentially, what ad hoc binding is that the value of x is provided by the caller. meaning the caller here is call at the point of calling, the value of x is 3, and that's what it's used. I'm sorry about the shifts there. Anyway, so now that we've looked at different kinds of functions and different kinds of parameters, let's look at different ways in which parameters can be passed. The first one is pass by value. This is the most obvious one. Essentially what this means is that whatever, when you're invoking the function, whatever the value of the parameters are, these are used to perform the computation and the values return. Let's look at an example here. There is a function f which takes in two parameters a and b, and the computation it performs is that b is assigned to a incremented by 1, and it's going to print both a and b. Now when you invoke f with x comma x, where x is 1, it's simply going to pass the value of x at that point of invocation, which is 1, which means the value of a is going to stay 1, the value of b at the start of the invocation it's still going to stay 1, but it's going to change to 2, and then what you get printed out is a is equal to 1 and b equal to 2. But since you only pass the value of x still remains the same. It is unaltered by what the execution of the function did to its internal variables itself, which means when you try to print x, it's just going to print 1. What we have to worry about here is also the order in which these values are evaluated. For example, take this function p of a, which simply prints a and then returns a. Now, what happens when you invoke f with p of 1 and p of 2? Is it going to print 1, 2 or 2, 1? This depends on in which order the functions are evaluated. Modern languages like Java, ML use the left to right evaluation order, which means you're going to get 1, 2. Again, I don't know examples of languages which use right to left. If you find out such examples, you're more than welcome to point out to me. Sorry about that. Languages like C simply leave it undefined, meaning the order in which these parameters are evaluated depends on the compiler itself. So essentially, the compiler writer has the complete power to decide how these are evaluated. Now let's look at another way parameters can be passed. This is pass by result. You can think of pass by result as the opposite of pass by value. Essentially, with pass by value, the caller, the value of a variable from the caller is assigned to the formal parameters, and then the computation happens. But with pass by result, also called out parameters, whatever the assignment happens from the callee back to the caller. Here, if we have an example of an out parameter, function f, which takes in one parameter a and an out parameter b, and then the same computation happens, and then you simply only print a here. Let's look at an invocation and what happens to the results of it themselves. So again, you have x assigned to 1. You call f with both x and x, meaning the value of x is bound with a, and then the value of x is also bound with the out parameter b, meaning whatever the value of b is after the computation is assigned back to x, and this would result in the value of x being 2 at the end of the computation, which is what is printed when you're done with your execution of the function. So that's pass by result. The other variant, before we go to the other variant, even with pass by results, you have to worry about the evaluation order, meaning essentially this is the order in which the results are assigned, right? So let's look at a variant of function f, where actually this matters. So we have function f, which takes in two out parameters. It assigns the first out parameter to a and the second out parameter to b. Now what happens when you invoke f with the same parameter x comma x, right? Whether is the value of x1 or is the value of x0? This again depends on in what order these out parameters are assigned. Languages like Fortran do it left to right, meaning the value of x will be 1, meaning because b is to the right of a. There is also the other variant where you can do it right to left. Languages like Ada simply disallow this, saying that, hey, you have tried to assign the same parameter to two out parameters, or same variable to two out parameters. I'm simply going to disallow this, right? So these are the impact of the evaluation order for pass by result. The other variant is called pass by value result. Essentially, this combines pass by value and pass by result, and these parameters are called in-out parameters. So here is a function which treats A and B, two parameters that it takes, as both in parameters and out parameters. It performs the same computation as the first variant we saw for pass by value and prints the result. To see how pass by value result works, let's look at a variant where x is assigned to 1, y is assigned to 1. And when you call f with xy, both of these parameters are in-out, meaning the value is passed, and whatever computation happens is assigned back again to the result. So essentially, it will print, of course, a equal to 1 and b equal to 2, but the value of y, which is bound to b, will be assigned back with the value of b, which is 2, at the end of the computation. So the next variant, which is very common with modern languages, is called pass by reference, right? This variant is generally used to speed up execution, or at least that's the claim, and they do speed up execution in many ways. First, let's look at an example before actually discussing what the difference is between pass by reference and pass by result, because that's an obvious question that will come up. Here you have a function which takes two reference parameters, a and b, does the same computation, and it prints the values. Now, again, the variant that we saw, the result is going to be the same as the variant that we saw for pass by value result, but the difference here is that the updates are effective immediately when you apply them, meaning the moment, so here y is, the reference of y is passed to b, right? Same way the reference of x is passed to a. The moment b is updated with, or the computation b equal to a plus 1 happens in your memory, the value of y, or the value that the reference of y points to, is updated to 2. Of course, this is going to be visible only when you perform complex computations inside. So for example, if somehow y is a global variable and you print y inside the function, it would print 2 already. But in the case of pass by value result, it would be visible only after the function execution is completed, right? So in most cases, the difference is not obvious. But again, as I mentioned before, pass by reference is one of the most common ways parameter passing is handled with modern languages. So now that you've seen pass by reference, a question would come immediately, right? Because when you pass a variable, you're only passing the address to that variable. What if you're calling the function with an expression which doesn't have a memory address immediately, right? In this example, you have a function which takes in one parameter and you call it with x plus 1. X has a memory location which can be passed, but when you pass x plus 1, there is no memory location. Languages like C++ simply disallow this, but modern languages like Java creates a temporary location for this expression and then assigns it, right? So this also leads to complications on what happens when you modify x in between, and this greatly varies depending on what kind of languages you use. The final variant of parameter calling that we will see, or parameter passing that we will see, is called pass by name. And before we look into with our example how it works, the reason why pass by name is supported in some languages is for you to be able to perform the same task multiple times. These are mostly useful when you want to compute equations like sum over xi star I and do this sum for all I from 1 to n. So for this computation, you would simply pass the name xi to the sum, and then which would just be replaced with the actual parameters. Let's look at an example of how this actually happens. Here you have a variable count equal to 0, and then there is a function which computes next, and then it increments count equal to count plus a, and then it simply returns count. To know why this is actually different from the pass by reference that we saw before, let's look at another function f which passes the name b, which refers to a function, like an indirect parameter, right? Indirect function calls. It prints b1 equal to b and b2 equal to b. In the normal variants, if you simply call f of next of 2, next of 2 will be computed first, which means the count will be incremented by 2 and then it would be returned. This would be passed on to f, which means that when you call f with next of 2, in a normal variant, you would simply get b1 equal to 2 and b2 equal to 2. But in the variant of pass by name, next of 2 is considered a name and it is simply replaced, or the code of the function, the body of the function simply replaces b with next of 2 how many ever times you use b. Meaning the definition of function f would simply change to print b1 equal to next of 2, comma b2 equal to next of 2. And every time next of 2 is called, the value of b is incremented by 2, meaning what you would get as a result is b1 equal to 2 and b2 equal to 4. Right? As I mentioned before, this is a variant of parameter passing that is used by languages which want to allow you to perform a computation or repeat a particular task multiple number of times. Right? So we saw different ways of parameter passing, and I already discussed a little bit how the implementation of these looks like. Now let's try to look at how implementation of parameter passing would look like in memory. Of course, there's a simplified diagram here. We're going to assume a function sub which takes in 4 parameters, a, b, c, and d. We are going to assume that a is passed by value, b is passed by result, c is passed by value result, and z is passed by reference. Meaning during invocation, when you provide w, x, y, and z, w is passed by value, x is passed by result, y is passed by value result, and z is passed by reference. Now let's look at how this would be implemented in memory. W, since it's passed by value, the stack will simply be updated with w, which would then refer to a at the start of invocation, and x, since it's passed by result, would be exactly the opposite of what happens to w, meaning x would be assigned the value of b, but this would happen only at the end of the function execution. When you pass by value result, essentially y, which is going to be the value of y is going to be put in the stack, which is then referred by c, but whatever happens to c is assigned back to the value of y at the end of the function execution. And the final variant is passed by reference. It is very similar to the pass by value result that we saw. The address of z is assigned to d, so essentially d points to the address of z. Computations happen, but any time you refer to the value of z during the execution, you are going to have the value of whatever has happened to d inside the function. So this is a brief overview of how parameter passing is implemented internally. Right? So now that we've discussed different kinds of functions, different kinds of parameter passing, different kinds of parameters, I want to end with a rather complex concept called closures, which is a variant of nested functions. This is, again, as I mentioned, it's quite a complex concept, so I'll just provide a glimpse of this in today's session. So closures are essentially functions which also have a referencing environment, and they can be considered a variant of nested functions. Nested function, so here we have an example in Python where you have an addx and a nested function inside add2, which only takes one parameter y, but it also gets the referencing environment from the enclosing function, which is add. Right? The difference here is that nested function definitions are themselves not closures. They have here x, which is a free variable which is not yet bound. Only once the enclosing function, which is here add, is evaluated with a value for this parameter for this particular variant, then the parameter, the free variable is kind of bound to a particular value. Right? So to see the advantages of it, let's look at an actual example. Here in this closures can be confused with anonymous functions, and they can be the same, but I'll provide you an example to show what the difference is between the two. Right? Essentially, closures have names, anonymous functions are lambdas without name. So here is a Python code. Here you have defined f of x, and then there's a nested function g of y, which essentially returns x plus y. And what f does is return a closure g, which is not yet bound, where the value of x is not yet bound. This depends on how you assign specific closures to variables that we'll see in a few lines later. So then you're defining h of x, which also returns a closure, but this closure is not named. So this is called anonymous functions. So essentially you're using the keyword lambda, which says that internally there is a function y, which computes x plus y, right? The only difference between the variant above and the variant below is that the lambda does not have a name, whereas the closure above has a name, which is g. Now, how you assign specific closures to specific values is that you create one variant of f and you call it a, but here you bound the value of x with 1. And you create another variant of b where you bound the value of x again with 1, right? So essentially a itself, a and b, can be considered variants of f and x with particular binding. You can define any number of variants of f with 2, 3, 4, whatever. One example of where something like this would be useful is you've defined an adder function which adds a particular value to the parameter that you pass, but you have different variants of them. You can have add 2, add 5, add 7, and if you call add 7 with a particular parameter, it's going to add that particular parameter's value with 7, right? Because you bound x with 7. Okay, and you can use closures stored in these variables simply by calling a. Now a does whatever f does, but it does f where x is bound to 1. So which means it would increment f by 1. B, as we see, are similar to a, but it just utilizes h of x. But because both of them do the same thing, it kind of doesn't matter here. It's irrelevant here whether your internal closure has a name or not. It's just to illustrate that these two are different, right? You can also use closures without giving them names. For example, you can say f of 1, which uses the version of g where x is bound to 1, and then you can call it with phi. Same with h also. So essentially, closures are nested functions where the value of the internal variables are bound, right? So, so that brings us to the end of today's session. We looked at what functional abstractions are. We looked at the different kinds of functional abstractions like methods and procedures and functions. We looked at how functions can be parameterized and how parameters can be passed, how it's dealt with internally in memory. We looked at a couple of different variants of functions themselves. And with that, I would like to thank you. Bye-bye.